All right, guys, we're back. Sorry to have that interruption. So hopefully you guys are watching part 2 of the video now, and this is kind of exactly where we left off. Um, so what we do is we have this equation here. You guys remember, do the auto ionization of water. This will, for any water-based solution, and you guys remember, if it's acidic, you're simply going to have a higher concentration of this than this, but nonetheless, the product, if you multiply them, will equal 1 times 10 to the negative 14. If it's a base, you're going to have a higher concentration of this than that, okay? And if it's a neutral, obviously those are the same. It's going to be 1 times 10 to the negative 7, 1 times 10 to the negative 7. So what we've done is we're just going to show, you can do a derivation, and you can take the log of both sides. And I wouldn't worry too much about this. I didn't even purpleize it. But then what you can do is, you guys should recognize, negative log of the hydronium ion concentration, isn't that the pH? And what's the negative log of the OH minus concentration? That's the POH. So you get the pH plus the POH equals the pKw. So that's just the negative log of this. You remember we took the negative log of both sides. Negative log of this is 14. So what you'll find is pH plus POH equals 14. So if I had the pH of a solution is 3, you guys know if it's 3, it's less than 7, you know it's acidic. Well, what's the POH? Well, we'll go 14 minus 3, it's going to be 11. And so a higher POH would indicate it would confirm that it's acidic. Okay, how do we measure pH? We can use litmus paper. You guys, litmus is just a substance that's going to have a certain color in. It's going to have a certain color in one pH, and then it's going to change color in another pH. It really uses a reversible reaction, like we've talked about before, like with mood rings, depending. But unlike mood rings, which changes based on temperature, litmus would change based on pH. And so you could use different pH, like for example, phenolphthalein. A lot of times this is the most popular one, phenolphthalein. It changes from like a colorless to a pink in the pH 9 range. So if it's less than 9, it would be colorless, and if it's in an environment where the pH is greater than 9, it would be pink. And so you can see probably the best one to use to determine whether or not you have an acid or a base would probably be bromolethyl blue, right? Because this is the one, if you guys notice, it changes color in the pH range of 7. So if bromolethyl blue was yellow in a solution, you'd think, oh, okay, that you would know, oh, that's an acid, okay? And if it was blue, that would indicate it's a base. More accurate measurements, we use a pH meter, okay? So you can actually get a digital readout. Chalupa, cheesy Fritos, gorditas, Doritos, Locos, Nachos Belgrande, impressive. But I still wouldn't say you're fluent in Spanish. Okay, here are the strong acids, guys. Notice this is in purple. This is what you guys need to remember, because if you just remember this, and notice obviously what's characteristic of all the acids, they all have hydrogen, okay? If you just remember the 7, any other acids you come in contact with, you know they're weak acids. So these are the ones that are going to completely dissociate. You put them in water, for all practical purposes, it goes to the right. The K value is extremely large, right? And so all other acids would have lower K values. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid. This is chloric acid and perchloric acid. You know what you could remember too, it helps. If you remember that all of these, right, you'll notice hydrochloric, hydrobromic, hydroiodic, those are all strong, so that helps. Sulfuric acid you're familiar with, that's in car batteries. And then these two you can see are very similar, chloric and perchloric acid. And then nitric acid is another one we talked about. Okay, these we'd call them strong electrolytes. You guys, by electrolytes, you guys have probably heard that with like Gatorade. You guys know with Gatorade, right, it's going to provide like potassium ions and sodium ions that are necessary for proper motor functions, right? That's what electrolytes are, kind of ions. The reason why we'd say it's strong electrolyte, because it's going to produce a lot of ions, right? You guys think about strong acid, completely dissociates. Basically, what are you left with? You're left with ions. Strong electrolyte, it's called electrolyte, right, because it's going to conduct electric current very easily. You guys remember, the higher the concentration of ions, positive and negative ions, the more conductive it is. So, for monoprotic strong acids, you're saying the concentration of the hydronium ion is essentially the concentration of whatever your acid was. Like for example, if this was 1 molar, you guys, essentially this is going to be 1 molar because it's going to completely dissociate. For every one of these, you produce one of those. So for all practical purposes, whatever the concentration of the acid is, you're like, oh, that's the concentration of your H plus or H0 plus ions. Strong bases, those are soluble hydroxides, so hydroxides that dissolve in water. So basically it's going to be metals with a hydroxide, OH minus. These are the alkali metals and the heavy alkaline earth. You guys here, you know what's going to help you here? Somebody taught me this. You guys are like, this is my periodic table, right? And you remember you got your two columns here. Basically, your strong bases are any of these, like you guys sodium, you guys your alkali metals, and then your heavy alkaline earth. Notice it forms a B. Here, I'll do it in blue for base. So basically what we're saying is, if you have sodium hydroxide, potassium hydroxide, rubidium, cesium, francium hydroxide, or radium hydroxide, barium hydroxide, strontium hydroxide, see how it kind of forms a B? If those are with OH minus, strong base, what does strong base mean? Completely dissociate. All right. So you guys see here, we got the same thing that we were showing up here. Okay, it's just showing a kind of generalized dissociation. So once again, you guys, if we do the K value, we take the products right over here. That is why the equilibrium, understand that's important. Over the concentration of the reactants. Notice the pure liquid water is not in there because its concentration isn't affected. It doesn't change, and therefore it's not going to affect the equilibrium constant. This equilibrium constant is called the acid dissociation constant. We call it Ka. You guys, Ka, A for what? Acid. Just like you remember with the one for the dissociation of water, we call it Kw. Same thing. It's just the K value. Okay, you get it the same way. Well, you guys should realize, this is important, when you guys agree, the higher the Ka value, the stronger the acid. That's essentially it. When you guys agree, you're going to have a higher value of this if you have a greater concentration of the products, which would indicate more dissociation of your acid. The higher the Ka value, the stronger the acid. The lower the Ka value, the weaker the acid. Here are some weak acids. You notice how you tell these are weak? They're simply not one of the 7. That's the easiest way to tell. And then, so even this is hydrofluoric acid. It's actually one of the stronger weak acids, and it's got a Ka value 6.8 times 10 to the negative 4. But you guys notice these values, these are all 10 to the negative 4, 10 to the negative 5, 10 to the negative. You guys see they're all relatively small, indicating that your product side is not as favored as your reactant side. Okay, you guys, we're going to end with a type of problem here. pH of a 0.1 molar solution of formic acid, HCOOH, at 25 degrees Celsius is 2.38. Calculate Ka for the formic acid at this temperature. So you guys, this is kind of pretty common. You guys, like chemists would want to know Ka values. In fact, you would look up in a handbook Ka values. So let's say you're a research chemist, you have some formic acid, you need to be able to publish what is the Ka value for formic acid. And then you can see we know the concentration, and then we were able to get the pH. pH is 2.38. You guys, right, we would just use a pH meter. We put it in the solution. 2.38. What do you guys know about formic acid? Duh, it's an acid. You know it's a weak acid, right? Because it's not one of the 7. Okay. All right. Let's see how we're going to do this. First thing I would do if I were you, I would write the equilibrium expression. Now somebody would say, well, Mr. Wilson, formic acid, how the heck am I supposed to know that's HCOOH? You don't have to know that. You know what? You could just do it with this. You just do it. Who cares what the formula is? All we have to know is that it's an acid, it's giving up the hydrogen. So I would just use this, and you guys see from this, wouldn't the Ka value be, I would just go H plus ion concentration times the A minus all over the HA. And you guys see, it doesn't really matter what the actual formula is, as long as you know this is the hydrogen ions, this is the conjugate base, and that's the acid. Okay, so you have that. Okay, so then you guys know to get the Ka, you're going to need to know the equilibrium values of all those. So you guys are probably thinking, how am I going to get the equilibrium values of all those? What are you guys going to use? You guys remember from equilibrium unit, we're going to have to use ice, right? So we can find, and you guys, so think about, okay, we can get the H3O plus concentration because we're given the pH, okay? So I'll remind you guys, right? Remember, pH is equal to you should have wrote this down, negative log of the hydrogen ion concentration. So what's the hydrogen? Oh, I don't know the hydrogen, I know the pH is 2.38. Here, you know what, I think they actually do it, I don't even know writing it. Okay, yeah, there you go. 2.38 is equal to negative log of this. So then the question is, how do I do that on my calculator? You guys, I don't want anyone to not do well in the class simply because you don't know how to use your calculator. So what I would do is, when you guys agree, don't you bring the negative over here, because I can divide both sides by negative 1. So I'm going to go 2.38. I'm going to make it a negative. I don't know if you guys can see that. And then the question is, now how do I the log of H3O plus equals this. So I'm not going to press the log button. Remember, it's not saying the log of negative 2.38. It's saying the negative 2.38 is the log of what I want. So what do? I don't do log, I do the inverse log. And you guys remember how you do that on your calculator. You press an inverse or a shift button. In this case, it's a shift. I go shift, log, and then I get my value. And so that'll tell me what is my value, log of what equals negative 2.38. Now, you guys think about it, when you do it, your value should make sense. You guys remember, we know it's an acid, obviously, because so what should I know about my hydronium ion concentration? Wouldn't you guys agree if it's an acid, shouldn't the H3O plus concentration be greater than 1 times 10 to the negative 7? Because you guys remember that's what it is at neutral. So let's see. I do it, and look, it is greater than negative 7. It's 4.2 times 10 negative. It's much greater. It's like 4 factors of 10 greater, right? You guys know 10 to the negative 3 is much greater than 10 to the negative 7. So this is the hydrogen ion concentration. Okay. Oh, and you notice it's also the conjugate base concentration, because guys, look, let's say we have this just this reaction here. For every one of this that breaks up, I form one of that and one of that. So those are going to be the same concentration. So I know that. So then I was thinking, you're thinking, oh, I need my ice table. Remember, this is the value they gave us. This is my. You guys see, this comes directly from the reaction. You guys remember? Here's my HA. Remember, it was plus water, but remember we don't include the water. And then it was the H plus and the A minus. You guys see, I didn't even have to write them exactly like they are. As long as I have a generic thing, I can do it. So it's 0.10. So before it dissociates, when you guys agree, the ion concentration is 0. Okay. Then, what did I just figure out from the pH? I figured out what the hydrogen ion concentration is. Because you guys remember, it was 4.2 times 10 to the negative 3. So that means that, and so remember, those were the same because it's a 1-to-1 ratio. And so what do you guys think? You guys like 1-to-1 and 1 ratio. So what is this? Wouldn't that be the same? That's how much of that is dissociating. 4.2 times 10 to the negative 3 and form those two. And then you guys, we show our results, right? So obviously, 0 plus that, 0 plus that is that. Now check this out. This is kind of important to know. If you guys do the math, if you guys do it, check this out. You go this times this, because this is such a small number, you're going to get 0.0958. But you notice we're already limited to 2 significant digits. So if you round this to 2 significant digits, what are you back to? 0.10. What do you guys notice? Essentially at equilibrium, the concentration of my acid is the same as it was initially. Not very surprising, guys, because it's a weak acid. You guys remember, weak acids primarily stay associated together. They don't ionize very much. So this is kind of something that will make life a lot easier for you. In fact, in my class, I'll let you guys do this. You shouldn't always assume this, but if you have a weak acid, for the most part, assume that the dissociation is so minimal that for all practical purposes, at equilibrium, you can just put the same concentration. It'll make everything a lot easier. So, you guys see? So now we took those values here. You guys see from the previous one, those equilibrium values, and we put them in the Ka expression. Hopefully you guys were following that. And we get 1.8 times 10 to the negative 4. This is the Ka value for formic acid. And you guys notice it's relatively small, which is not surprising because it's a weak acid. Almost done here, guys. One last thing. There's times where you're going to have to include what's called the percent ionization. You just want to know what, because obviously the greater, what would you guys expect? The strong acids to have a very high percent ionization. That's the percent of all of the substance that dissociates. And weak acids would have a small one, right? So you guys see, in typical percent, you guys remember what I said a percent is? It's a part over a whole times 100. That's essentially it. You guys think about it in this reaction here, right? There's just showing the dissociation of an acid. Just get in the habit of writing this generic form here. You're going to take, and you notice, and please, I know you're probably getting a little confused when you see H plus and H3O plus. Remember, that's the same thing. Technically, it's H3O plus, but we typically just write H plus. I mean, you could look at it you could just look at this reaction if you wanted to. But you guys notice, so I want to know, what percent of all this, of the acid, ionizes? So I take the part, because this would be the part that dissociates, and I divide it by the whole. So whatever was the concentration of my acid initially, I'm going to divide the H plus concentration that is formed from the whole. So it's a part over whole. Okay, so in this case, using the one that we just used, our hydronium ion concentration was 4.2 times 10 to the negative 3. Remember that from the ice chart? And I divide that by 0.10. And what are you going to get? Oh, and then I multiply by 100, and you do that, and you're going to get 4.2%. Once again, that just confirms what we expected. Pretty minimal ionization. In fact, if you have less than 5%, you pretty much think for practical purposes it didn't ionize very much. You kind of use 5% as the threshold. All right, guys. I know it was a lot. Try to digest it. Once again, maybe by the third or fourth time I'll start sinking in. All right, guys, we'll see you.